It's my pleasure to introduce Aiden and Ajay, who are both PhD students at Stanford. And they've been working on some quite interesting things, which is how do you communicate and sense across interfaces? In particular, if you're in the air and you're trying to see or sense or communicate with something which is underwater, how do you do it? So Amin is going to talk about some of the work they've been doing recently on achieving this. And with no further delay, Amin, the floor is yours.
Yeah, thank you for the introduction. Yeah, I'm excited to be here today to share some of the work that we've been doing in the Arbabian lab at Stanford. And I'm here with my co-author, Ajay, and he is the primary contributor to a lot of the device and circuits aspects of this project, and he may chime in throughout the talk to answer any related questions. Today I'll be talking about a photoacoustic airborne sonar system for underwater remote sensing and imaging. And the goal of this project, and I'll discuss this in detail throughout the talk, is really to image underwater from an airborne system. And to kind of provide somewhat of a high-level overview of the talk before I get started, first I'll motivate underwater imaging by introducing some of its key applications. I'll discuss some of the existing imaging modalities for remote sensing, such as sonar, radar, and LiDAR, and I'll touch on the limitations of these modalities for our application, which again is imaging underwater from an airborne system. And then I will introduce the concept of our system, photoacoustic airborne sonar, which we have coined PASS. And I will break down PASS into kind of its subsystems to explain how it works. I will show some of our early experimental demonstrations of the system. And then lastly, I will conclude by providing an outlook for the path to field deployment of this system and outline some of the remaining research challenges that must be addressed. Like I said, there are many applications of underwater imaging, and I'm just going to name a few here. And the first being exploring and mapping uncharted waters. And this is an essential activity for things like navigation, oil and gas exploration, pipe laying, among others. And then there's surveying biological environments, for example, studying biological processes over time, such as monitoring coral reefs. Wreckage searching, such as looking for sunken ships or aircrafts. And like I said, this is just a select few applications. And in addition to this, scientists are really just interested in understanding more about the oceans of our planets that we have really only scratched the surface of. And to drive that point home a little bit more, I have a few stats listed here that I find extremely interesting. So despite the fact that ocean covers greater than 70% of the planet's surface, over 80% of that has been unmapped, unobserved, and unexplored. And even if we take a step back and we think only about coastal waters, only 35% of US coastal waters have been mapped. And I want to draw special attention to this last bullet because I find this one extremely interesting and one that our system might be able to help overcome. So there are 43,000 square nautical miles of US waters considered critical to navigation, yet only 2,500 or so of these are surveyed annually. And this means that there's really low temporal sampling or sampling over time. And this puts our maritime transportation system at risk to hazardous obstructions along these critical navigation routes. So clearly there is a technology gap here. And this is why our goal is to develop a high throughput imaging system that allows for larger coverage so that we can reduce that 80% stat and have higher temporal sampling so that we can more often monitor these critical navigation routes. Okay, so now that I've kind of motivated underwater imaging and the need for a high throughput imaging system, let's take a look at some of these existing imaging modalities and their limitations for achieving this. So first there's the sonar, which is an imaging modality that is widely used in our oceans today. And sonar systems are typically mounted to or towed by ships that traverse an area of interest. And this allows for them to image the underwater environment as you can kind of see in this image here, albeit at a relatively slow rate. And this limits really the spatial coverage that, that can be covered by these systems, and contributes to the gap in the statistics that I previously mentioned there. So just to kind of reiterate, our goal is to develop an airborne technology with the versatility to be deployed, possibly on helicopters or on drones, to survey coastal waters with high temporal sampling and with larger spatial coverage. The first question, the naive question, I guess, that someone might ask is, can we simply take one of these sonar systems that is a really well-developed technology, and can we simply mount it on a sonar, can we rather mount it on an airborne vehicle, such as a helicopter or a drone? And to think about that a little bit more, let's take a look at, airborne ultrasound. So sensing systems that exploit sound waves in a similar manner as sonar are increasingly being deployed in airborne applications. And one of the most prominent examples of this is in modern cars. So airborne ultrasonic sensors, as we know, is just one of several types of sensors in the modern vehicle sensor suite. And they're typically used for the close range applications, such as parking and rear object avoidance. So, something we see here is, these sonar systems or sound-based systems can operate both in air and in water. So again, I asked the question, can we use this existing and well-developed sonar technology for airborne imaging of underwater? And the answer is no. Unfortunately, we can't do this. And this is because only a small fraction of the sound that is incident on the water surface actually makes it through. And what happens is most of it is actually reflected off of the water surface. And for me, I like to think about being underwater in a swimming pool. And hopefully some of you guys can relate to this analogy. But if you're underwater and someone out of the water calls your name, you likely won't hear it unless they're yelling pretty loudly. And for this sonar system, not only does the sound that transmits into the water lose a lot of energy, but also the sound that will reflect off of the object and need to come out of the water to hit our receivers will also lose a lot of energy. So basically here, for this kind of system concept, the sound would now need to travel through the air-water interface twice. And this reflection loss that we see would be so large that it wouldn't really be practical. The sonar system would need to be yelling so loud that it would really be unsafe and impractical. So now we can take a look at radar, which radar systems have been deployed on both satellites and airplanes and have produced high-resolution mapping of the entire Earth's landscapes. So we can ask, can we use radar to image underwater? And again, the answer is no. And this is really because the radio waves at frequencies useful for imaging are absorbed in the water, in the first few centimeters of the water. And this is different from the sound waves. I want to kind of contrast them a little bit. The sound waves reflected off the water surface, versus for the radio waves, they will actually pass through the water surface fairly easily, but then the water actually absorbs them really quickly, and they don't penetrate to large depths. And something to think about here is, despite the fact that cell phones are now waterproof, you won't have much luck getting a signal underwater. Okay, so in addition to radar, LiDAR has also been deployed on airplanes and on satellites for landscape mapping. But what I think is what most people might think about when they think about LiDAR is how it's becoming a major player in autonomous driving. And people in this space know that one of the major criticisms of LiDAR is that it has poor performance in rain and fog. So let's think about standing on a pier and looking down into the water. What do you see? If the water is super clear, maybe we can see a couple of meters into the water, but most often And probably for the water depicted here in this image, the answer is going to be you can't see much. And this is because, similarly to the radio waves, light is absorbed by the water, but a little bit less so than the radio waves. And that's what allows for penetration to, or allows us to see to a couple of meters in the water if the water is really clear. But what happens is when the water is murky, which it often is, light scatters off of the suspended matter that's making that water murky, which further increases the effective attenuation of light and reduces the penetration depth that light can reach in the water. So while active LiDAR systems can see further into the water than we can see with our passive visual systems, the scattering nature of the seawater is really what prohibits LiDAR from being a widely deployed solution for imaging underwater from an airborne system, as we are trying to accomplish. So, from what I just showed, if sound waves, if radio waves, and light all struggle to image underwater from an airborne system, how can we accomplish this? And what we're suggesting is that this can be accomplished using PASS, photoacoustic airborne sonar. I'm going to show a quick 30-second video clip of how our system works on a high level before I'll dive in later in the slides and kind of explain it piece by piece.
We developed a way to combine light and sound using the photoacoustic effect to image beneath the water surface from an airborne system. Our system uses a laser to fire a burst of light. This light is absorbed at the surface of water, creating sound waves. The sound reflects off of underwater objects, and a small fraction is able to pass through the water surface. We receive these sound waves with highly sensitive custom sensors and convert their energy into electrical signals. Using our developed computer algorithms, we reconstruct 3D images of the underwater environment.
So effectively, what our system is doing is we are creating an underwater sonar source from the air by leveraging the ideal propagation of light in air, and then relying on the propagation of sound underwater. So we're kind of taking advantage of the best of both worlds, where we can use the light, the laser in air, and the sound in water. So, like I said, now I'm going to kind of go through it piece by piece and try to explain the system in a little bit more detail. So first, a laser is used to create the underwater sound waves by means of the photoacoustic effect. So the photoacoustic effect is a widely used phenomenon in an up-and-coming biomedical imaging modality. And it's kind of depicted here in this figure. So for biomedical photoacoustic imaging, a pulse of laser light is directed towards the body. The laser energy will mostly pass through the skin, and will be absorbed by blood and other optical absorbers in the tissue. And the absorption of this laser causes a local temperature increase of the blood or of the optical absorber, and that will cause the blood to thermally expand. And the thermal expansion results in a propagating pressure wave or sound wave. So you can see here in this GIF here that the center thermally expands, and that causes a propagating wave to travel. And these sound waves are captured by transducers or ultrasound detectors, and then are processed to reconstruct an image of the body or what's in the body. For our system, I already discussed that laser energy is mostly absorbed by water and does not travel far into the water. And for that, we can't rely on the underwater objects that we are trying to image to absorb the laser energy to generate this photoacoustic signal, as was the case in the biomedical application. Instead, what we do is we carefully select a laser wavelength that absorbs nearly completely at the surface of the water. Then what happens is the water itself thermally expands and creates a sound wave that will propagate into the water. And what's really great about this photoacoustic effect is that it's linear with respect to the laser power. So this allows for us to intensity modulate the laser to create sound waves at desired acoustic frequencies.
Very quick question here. If you're thermally heating up the water, do you need the water to be still for this effect to show up, or will it work even if the water is wavy and the waves on the water?
Yeah, so the process of the thermoacoustic effect is so it happens so fast, on the order of microseconds or less. So in terms of will the sound waves be generated if the surface is not static? Over that time scale, the surface is approximately static. It doesn't move very much over that time scale. But what I will talk about later is that these waves will become challenging to deal with in terms of the image reconstruction process. But in terms of the actual sound generation, there's little effect that the waves will have.
Thanks.
Yep. So like I was saying, the great thing about the photoacoustic effect is that we can intensity modulate the laser to generate acoustic waves at any desired acoustic frequency. As you can see here, we have one pulse of laser light, we get one wave front, versus if we have 3 pulses of laser light, we can get multiple sound waves. And this allows for us to concentrate the sound waves at desired frequencies. And I'll circle back to this because this will become really important later in the slides.
Quick question: when you say intensity modulate, you're saying here you can change the frequency by sending multiple pulses, but can you also change the amplitude as well?
Yeah, so we can have, there's some advantages which I'll also talk about later. So you can have, you can control the amplitude of the laser power as well as the frequency of the modulation to really have precise control over the sound waves that are generated underwater. There's a lot of advantages in imaging systems and in communication systems that this will have for us. Okay, so now that we have generated the underwater sound using the laser and exploiting that photoacoustic effect, let's take a look at how the sound propagates underwater and interacts with these underwater objects. So sound propagates as a pressure wave. So with no external stimulus, molecules in a liquid, a gas, or a solid are arranged with some degree of density. And a time-varying pressure wave is imposed on this, as is shown in this picture here, where peaks in the pressure wave are regions of compressed molecules, and troughs in the pressure waves are regions of rarefaction, or where the molecules are less dense. And the speed at which this pressure wave will propagate and travel outwards in space is dependent on the medium that they exist in. So for example, sound waves travel significantly faster in water than they do in air, which are the 2 media of interest for our application, because we generate the sound waves underwater, but we will also have to detect them in air. And here I show a little bit a quick simulation of what happens when we generate these sound waves underwater, and they reflect off of just these 3 targets that exist, or objects that exist underwater. So at the surface, the laser excitation generates these sound waves. They propagate out in a spherical wave pattern, and they reflect off of the underwater objects. And the amount of pressure that reflects off of these objects is dependent on what's called the acoustic impedance. So the acoustic impedance of an object is dependent on the mass density of the material of the object, as well as how fast sound travels in that object, the speed of sound. So for example, the acoustic impedance of water is 1.5 megarail, or 1.5 million rail, where rail is the unit for acoustic impedance, as ohms is the unit for electrical impedance. And the amount of pressure that reflects off of the object can be quantified by calculating this reflection coefficient gamma, which essentially is how different is the acoustic impedance of the object to the acoustic impedance of the medium that the sound waves were originally traveling in, which in this case is the water. So I've included a table here with some common materials. So to kind of tie it to an application, for the application example of searching for shipwrecks or plane wrecks, aluminum, the most commonly used metal in airplanes, reflects about 84% of the pressure that is incident on it. Whereas materials used in boats and ships, such as steel, wood, and fiberglass, reflect 94, 33, and 65% of the incident pressure. And the more pressure that reflects off of the underwater object, the easier and higher chance of detection for our system. Okay, so now once these acoustic waves reflect off of the underwater objects, they will travel back upwards towards the water surface, where here the water surface will also be kind of a mechanical discontinuity or mechanical boundary where the sound will reflect off of. So some of the sound that travels up will reflect off of the water surface back into the water, whereas some will transmit through the air-water interface, and these are the ones that we hope to detect for imaging. I'm going to take a closer look at it here. So recall that the acoustic impedance was equal to the density of the medium times the speed that sound travels in the medium. And air we know to be significantly less dense than water, and sound travels significantly slower in water than in air. So this results in an acoustic impedance in air of only 420 rail, orders of magnitude lesser than the acoustic impedance of water. And like I said, the reflection coefficient is how different are these acoustic impedances, and that results, which shows here that the reflection coefficient is 0.99944. So this means that 99.94% of the sound that hits the water surface reflects back into the water, and only 0.06% transmits through the water surface into the air. And this is what we are hoping to detect, these really significantly dampened acoustic signals. And this will require extremely high sensitivity detectors in air or receivers in air. And this is what I'll talk about in the next slide. But first, I want to mention that in addition to the large loss, sound waves that are incident on the water surface at oblique angles will also have wave refraction as they leave the water. This wave refraction is something that is very deterministic, and it can be calculated using the well-known Snell's law, but it is something that needs to be compensated for, and it does in some ways complicate the image reconstruction process.
So I have a quick question here. If you're saying that you have the ability to, you have hardware which is mobile enough to detect these very tiny signals which get through to air, I understand what you guys are doing with imaging, but does that mean that you can use that hardware also to communicate from the air from a device which is under the water, which is using acoustics?
Yeah, so that's an application space that we're currently working on right now, and it is interesting because there really is no robust solution for communicating between nodes in water and nodes in air. So this is an interesting technology that might afford us that capability that is not something that is easily done today. So yes, I think the short answer is yes, that is something that we can do.
Cool.
Okay, so now those significantly dampened acoustic waves will continue to travel in the air, and they will be detected by our ultrasound transducers or receivers. In this case, we are using CMUTs. So CMUTs, or capacitive micromachined ultrasound transducers, were initially invented by our collaborators at Stanford about 2 decades ago for contact-based imaging or traditional ultrasound imaging. And since, our collaborators have been working on designing these CMUTs also for airborne applications. And they do this because these are devices that offer really great sensitivity. And this sensitivity really helps us overcome that large loss or that large dampening of the signals that is encountered as the sound waves leave the water and travel into the air. But what's also interesting about these devices, and is really advantageous, is that they are fabricated on silicon, which makes it easy to integrate them into large arrays, and to also integrate them with supporting electronics. So for imaging, it's important to have an array of receivers. And this technology is something that is really scalable to hundreds of elements in an array of transducers. So the working principle of the CMUT is shown kind of by this GIF here. So as the sound waves impinge on this top plate of the CMUT, the plate is flexible and it will deflect. And these devices can be modeled as a capacitor. So when the plate deflects, the device capacitance changes because of this relationship shown here. And what we do is we interface the CMUT with circuits that effectively detect this change in capacitance over time. And this basically converts the acoustic waves into the electrical signals that we can exploit for imaging. The disadvantages of these CMUT devices is that they have a very limited bandwidth, meaning that they only respond to sound waves that are within a very narrow range of acoustic frequencies. And I say this is a disadvantage, but there's a little bit of a caveat here because this is actually what helps to achieve that extremely high sensitivity. So any signals, any ambient noise signals that are outside of the frequency range of these devices will get rejected. And that makes it easier for us to detect signals of interest that are at the acoustic frequency that these devices operate at. But really where the disadvantage comes in is that having a narrow bandwidth means that your imaging resolution will suffer. And I'll talk about that on the next slide.
Quick question, when you say these are narrow band, like how limited are we talking?
So this plot here shows the CMUT device frequency response. And this is for the specific device that we are using currently. So the device has a center frequency of 71 kilohertz and a bandwidth of only 3 kilohertz. So this is a fractional bandwidth of 4%. And a device with such low bandwidth is called a resonant device. And just to kind of put this into perspective, typical acoustic imaging systems, whether it be sonar or conventional contact-based ultrasound, they use devices that have a fractional bandwidth of greater than about 50%, and they do this to achieve high-resolution images. So to understand the relationship between bandwidth and resolution, I want to make an analogy to a playground swing or a pendulum, which is also a resonant system. So imagine if you were sitting on a swing, but you have yet to begin pumping your legs. And by pumping your legs, I mean, doing this action that this figure is doing here. And so you're sitting still on the swing, and first you pump your legs once. The swing will move a little bit, but not much. Next, you pump your legs 5 times. This will be enough to get the apex of your swing to a reasonable height. But after these 5 leg pumps, let's say you sit still on the swing, no longer pumping your legs. The swing will continue to swing back and forth until eventually you come to a stop. So now let's take a look at this figure. If one cycle is incident on the CMUT, if one acoustic cycle hits the CMUT has some response, but not much, similarly to if you pump your legs once on the swing. On the other hand, if 5 cycles are incident on the CMUT, then the CMUT will ring up to a reasonable signal amplitude. But once these 5 cycles have ended, which is similar to you no longer pumping your legs on the swing, the CMUT has a gradual decay in its signal amplitude back to 0. So what this shows here is that these 5 cycles, having many cycles at the resonance frequency of the CMUT at the 71 kilohertz, is required to kind of bring this CMUT up to having high signal amplitudes, being able to detect the signals. But this gradual decay, or this tail, reduces the imaging resolution. And that's because if signals were to arrive at later times, say a signal arrived here, it would get occluded by this tail. It would be interfered, this tail would interfere with signals that arrive at later times. And that effectively will reduce the resolution of your imaging system. So to combat this trade-off, we have adapted a signal encoding technique. So basically, if we take these 5 acoustic cycles that are needed to ring the CMOD up to reasonable amplitudes, and we follow that with subsequently timed cycles, we can cancel or suppress the residual decaying tail of the CMOD response. And to kind of bring this back to the playground swing analogy, let's say this is equivalent to somebody basically grabbing the swing and pulling it forward while the swing is moving backward and pushing it backward while the swing is moving forward until the swing comes to a stop. And basically this external force will cause the swing to come to a faster stop than if you were to just sit there and wait for it to come to a stop. And this technique is what really has allowed us to exploit the high sensitivity of these resonant devices, these narrowband CMODs, while maintaining reasonable resolution by canceling or suppressing this residual tail. And to circle back to the laser excitation of the sound waves, it's really the linear nature of the photoacoustic effect that allows for us to control the sound waves to not only ensure that these sound waves exist at the 71 kilohertz acoustic frequency, but also allows for us to encode the transmitted signal with these suppression cycles that will help improve our imaging resolution.
Aidan, do you want to take some of the questions in the chat?
Oh yeah, of course. I haven't been monitoring it. That's a good point. Okay, so how much filtering of the rotor blades do you have to do for the CMODs? I would imagine the harmonics of the rotor blades would be very loud in comparison to the acoustic. So this is something that is possible. There is the chance that whatever the airborne vehicle is, there may be acoustic signals that fall within the band of our imaging signals. So what we could possibly do, and something that we have started to look at, is to encode basically have the transmitted signal have a coded pattern such that we can do what's called match filtering and basically look for these signals that we know we transmitted in the received signals. I don't know if I said that.
But that's potentially going to reduce your throughput, right?
It could potentially reduce the throughput. Yeah, that's true. But the signals are relatively short, so I don't think it would significantly impact the throughput. I mean, the throughput is mainly limited right now by waiting for the propagation time. So the acoustic signals, because they travel a lot slower than, say, electromagnetic signals, you have to wait to receive these signals. So really the throughput is limited by that, and not so much by your transmitted signal. So I think we have some time to play with, I think, to send coded signals and do this kind of match filtering to look for the signals that we are sending and get around having some of these noise signals that may fall in band of the device of the receivers. Okay, so I explained kind of the concept of having a single CMOD, but as I mentioned earlier, the CMODs are great for scaling them to arrays. And in imaging system, we need to get spatial information that is acquired by having an array of receivers. And so basically each of these receivers in the array detects a signal, like I showed on the previous slide. And these signals are what we pass to the signal processing pipeline in which the image reconstruction is performed. So here I'm going to explain an example image reconstruction algorithm. This is not the image reconstruction algorithm that we use. We use one that is more computationally efficient. But I think this is a good exercise because it helps to understand the relationship between the received signals and the reconstructed images. So first, let's consider the imaging geometry we have here, where we have an array of CMOD receivers and laser excitation that exists in the center of the CMOD array. I'll explain this algorithm in 2 dimensions, though it's important to keep in mind that the same thing can be extrapolated to a 3-dimensional equivalent. So the goal is to reconstruct an image in the water. So the first thing we do is discretize the water into pixels. We must access the received signal at the first receiver. Then we can access the image value at the first pixel, where the reconstructed image is initialized to be empty or all zeros. We can then calculate the time of propagation from the point of laser absorption to the pixel to the receiver. And let's call that time t1. Finally, we can sample the received signal at time t1, and we store this value, or we add this value to the original value in the reconstructed image. And we do this, we loop over all of the pixels in the image. So we'll loop over all of these pixels and do the same procedure. So for example, when we get to this pixel here, we can calculate the propagation time from the point of laser absorption to the receiver to be dw1, this distance here, divided by the speed of sound in water, plus dw2 divided by the speed of sound in water, plus dA divided by the speed of sound in air. And again, what we do, so let's call this time t2. So then what we do is we'll sample the signal at time t2, and we'll add this value to the value in the image. And it's important to note that here, you see that we have accounted for the refraction at the interface when finding the propagation distances. And finally, what we do is we'll loop over all of the receivers. So this process has to be repeated for all of the receivers in the CMOD array to be able to reconstruct the final image. And this algorithm is often referred to as the time domain back projection algorithm, and it has a lot of similarities to the delay in sum algorithm that is used in conventional ultrasound imaging. And I think something that you can note here is that it's clearly pretty computationally expensive. You have to loop over all the pixels and all the receivers, and it becomes expensive to do this. So as I mentioned before, we are using an algorithm that is more computationally efficient. So where this algorithm works in the time and space domains, our algorithm works in the frequency and spatial frequency domains by taking Fourier transforms over the signals. And this exploits the computationally efficient fast Fourier transform and significantly reduces the computational cost of performing the image reconstruction. And I'm not going to go into more detail about how our algorithm works, but I do provide a full derivation of it in my most recent paper.
So a couple of questions we have. Alex had the question about movements of the UAV and it vibrating, the UAV is vibrating with wind and so on. So when you evaluated these things, was this evaluated on a UAV or are others actually evaluated with just a static platform?
Yeah, so I will show some experimental results and I'll explain our experimental setup in a couple of slides, actually the next slide. But we are doing it with a static platform and we're not currently operating the system on a UAV. When it comes to running it on a UAV, these are definitely concerns that we will have. But these are also concerns that are being addressed in radar imaging. Now that we have moved in the radar imaging world, now that we've moved to millimeter wave, we have the same problem where we have really small wavelengths and the vibration and movement of the platforms is a really important problem. So this is something that is being actively researched for solving this, whether it be using things like SLAM algorithms and other computational workarounds for getting around these vibrations is something that we will likely have to employ as well for this system.
So another question which I had is, so in this particular formulation, you could write the diffraction equations because you know the surface of the water and so on and so forth. The couple of things which come to mind, the first one is with waves, the surface itself can change. The second thing is, what if you have suspended particles in the water itself, like dirt and just particles, which can scatter the signal? How would, and that's pretty hard to basically account for at least deterministically. So how would you basically think of addressing these issues?
Yeah, so I think one thing I like to think about is optical imaging. So you talked about the scattering of the waves as they travel through the water, whether it's off of particles or whatever. And this is an active area of research in, say, optical imaging for like the brain imaging, for example, functional brain imaging. So when light enters the body, it has the same effect where it diffusely scatters. And that obviously complicates the image reconstruction. But here, where we have in the water, where you have acoustics, the wavelengths are typically much larger than these particles. So the scattering is less impactful. So you can basically, yes, some of this energy is going to scatter, but we rely on the paths that are basically the ballistic paths, the paths that are not scattered to do the image reconstruction. So the ones that follow this ray tracing. But yes, so basically what it comes down to is because the acoustic wavelengths are larger than these particles that may do the scattering, it's not too impactful. But your other question with regards to the water surface, and yes, here we can calculate the refraction clearly. Our other algorithm that we use, the frequency domain algorithm, you don't have to explicitly calculate this refraction. It's taken into consideration through the dispersion relations of the respective media. So this is something that's kind of inherently taken into consideration through the mathematical formulation of our other algorithm. So what it comes down to is we don't necessarily need to say, okay, what is the angular refraction at each point on this wavy surface? But what it comes down to is we have to have a decent estimation of what the surface looks like. So this is something that we are trying to overcome with computational algorithms to basically try to optimize, basically as an optimization problem where we can say, let's find the wave pattern that makes our image reconstruction effective. And all of the refraction stuff is lumped into the image reconstruction process and is inherently taken into consideration through the mathematical formulation.
We have one question before we can let you move on from Astitla, who was asking, will multi-frequency laser change how reconstruction is performed?
So I think this could be taken two ways, multi-frequency being the wavelength of the laser or in terms of the intensity modulation.
Yeah, so I think this is partly related to an answer I gave about just using multiple ultrasound frequencies actually to increase robustness of our system. So we will, for this system, actually just use a single laser wavelength that turns out to be optimal, like Aiden discussed, where we just want the laser to be absorbed in the first few centimeters of the water surface. And then we might use multiple ultrasound frequencies by modulating the laser at different frequencies to get more robustness for environmental noise or interference from the environment. Also, to just add on a bit to the previous question as well about particulate matter that is suspended in water, I think one thing we should stress here is that we're not trying to reinvent the wheel when it comes to actually doing sonar imaging in water. There's such a large body of literature and work that already has been done and is being continually done, even using autonomous vehicles underwater, where they already deal with all these challenges in terms of sound-based reconstruction when you have murky waters or particulate matter that is suspended. So we would just adapt what people are already doing or have done in decades prior when we do run into those issues.
Now we've kind of covered the system from the laser excitation to the image reconstruction. So let's take a look at some of the experimental results. But first I want to show a view of our lab setup. So on the left here is a schematic view, and on the right is a true lab environment. So they're numbered here. So to kind of go through the chain of the system again, the first thing is the laser fires a burst of light. This light is intensity modulated at the acoustic frequency so that we can generate acoustic waves at the desired frequency. This mirror reflects the light down towards the surface of the water. That's not too important. And then the light is absorbed at the surface of the water. The sound is created, it propagates, it reflects off of the underwater targets, and some of it, after encountering that large loss, is received by the CMUTs in air, where they're converted to electrical signals, and these signals are digitized, and the signal processing is done digitally on a computer. And the last thing that's shown here, 7, it's not shown in the schematic, but it's shown here in the lab setup, is right now we are currently operating with a single CMUT device. We don't have access to an array of CMUTs. And like I mentioned, we need an array to get the spatial information in order to do imaging. So what we do to get that spatial information is we mimic the capture with an array by mechanically scanning this CMUT device. So we'll take a measurement, then we move to the next point, we take a measurement, we move to the next point. So, right now the image capture process is time consuming, might take 10 minutes to capture an image. But that is something that could be done simultaneously if we had the resources to build a large array of these CMUT devices. So the target being imaged in our experiments was an S for Stanford that was made out of metal rods. This S was placed at 18 centimeters depth in the water tank. And really this depth is limited by the dimensions of the water tank and not so much by the fundamental limits of the system itself. And I'll circle back to this in a slide or two when I'll talk about how deep our system can actually image. What you can see here, though, is I think a really high quality 3D image reconstruction. The artifacts are minimal, the contrast is high, the resolution is sufficient, and this is a result that we are really excited about, especially when we note that there is still much work to be done to optimize this system. So the path to field deployment. So finally, I'd like to show some predictions about the future performance of the system, and I'll talk about some of the remaining challenges that must be tackled prior to actually deploying the system in open water environments. So how deep can this system image? So currently, our proof of concept system that is by no means optimized theoretically has the ability to image as far as a few meters in the water, maybe the depth of a swimming pool. But we are using a suboptimal laser wavelength. We're using relatively low peak powered laser, and we're using an early generation of the airborne CMUTs that are not at maximum possible sensitivity. So to kind of interpret this plot here, it's the SNR of the signals or the image as a function of the target depth. So the depth in water that we can image. And we're basically saying anything over 0 dB, we should be able to get a decent image out of. So maybe, each line here corresponds to a different height of the receivers in the air. If we have the receivers relatively low in the air, we may be able to image as far as maybe 5-6 meters in the water. But that's with our system right now. So I want to make some predictions on what could be possible. So here on the right, I plot what would be possible with components that are actually attainable today if we were not restricted by resources. So this plot assumes a laser that is operating at the optimal laser wavelength. It is using a laser that is of slightly higher power, and it's using our newest generation of airborne CMUTs that we have yet to actually start using experimentally, but that offer significantly higher sensitivity than the ones that we are currently using. And what you can see here is that even with technology available today, we could image as deep as 100 meters in the water. And with the airborne CMUT technology being so young and the laser technology continuing to rapidly advance, we think that there's a lot of potential for this system to scale to even greater depths in the water.
This graph is great. So let's focus on this a little bit more so we can understand it a bit. So I know that the hardware you have basically has 71 kilohertz. Can you talk a little bit about what happens if if you're not limited by the specific hardware, what would be the exact frequency you would use though?
So there is let me see if I have that slide here. Okay, so here's an example of what you're asking for here. So the frequency that we use is a function of mostly the receiver height in the air. Because the acoustic attenuation in air is relatively high, you can see here that here's a plot of attenuation in air, this left, as a function of the frequency. And you can see that the attenuation is pretty high, as high as 9 dB per meter at 200 kilohertz. So really it comes down to you want to use lower frequencies to minimize the attenuation of the acoustic waves in air. But the receiver height is what kind of dictates what is the optimal acoustic frequency to use. So for example, let's say we want to have the receivers 5 meters above the water surface, we would want to use 40 kilohertz frequency. Versus if we want to be at 20 meters, we might want to use a 20 kilohertz frequency. So it really is, this is something that we have done the analysis on, and this is like something that we could use in the future to figure out what frequency to use. And what's also interesting about this plot is maybe it's something that can be dynamically used. So for example, you're flying your system out on the water, and at one point you're flying at 3 meters above the water surface, and you might be operating at 80 kilohertz. But then you say, okay, I want to move my system to higher heights in the air. You could dynamically adjust the frequency to, say, 20 kilohertz. So I hope that answers your question.
So the other question which Thorn asked is...
I have a question.
Go ahead.
I had a question regarding the receiver's height. If transmission is easier at a lower height, then would it be easier to use something like a drone or something that glides on the surface rather than something at a larger altitude? Simply because it would be easier to reduce the frequency losses?
So I think there is definitely an advantage depending on scenarios where you can deploy a system that is much closer to the surface of water. We would definitely go with that. There are no inherent advantages in terms of the technical capabilities of the system in flying higher over the surface of water. So where it is possible, we definitely would deploy a system, whether it's a drone or something that almost glides over the surface of water. But there are a lot of scenarios where something like this is not possible. Also applications where the added receiver height might give us better spatial coverage as well.
Okay, thank you.
That actually does make sense. I would assume that the height you would want typically might depend on the waves on the surface. If you want something to just like go.
Yes, it would depend on the waves of the surface. In some cases, like I would just say that our project, for example, is funded by the Office of Naval Research, that is under the Department of Defense. So you can draw your conclusions from that as well, but there are scenarios where it is just not practical to have something actually fly very close to the surface of water. So as Aidan mentioned, there are many different applications in this space that the concept of operations will change depending on exactly what you're using it for. Whether you're using it for something like kelp farming, maybe you can obviously deploy it very close to the surface of water and have dynamic measurements over time. On the other hand, if you're doing a lot of surface mapping or remote sensing, then you would possibly fly higher just to get advantages of remote sensing. So I think this is a question that will be very application specific, and the application itself also has to be more tailored than just saying that we're imaging something underwater.
Another question which I think Thorn had, which is about the fact that oceans, at least when you get far away from the coast, are pretty deep. How do you so I'm assuming that the application should be some place like, I'm assuming that a submarine or something is like 100 meters deep. You can use this to figure things out, but can you talk a little bit more about how you reconcile the fact that the oceans are much deeper than these depths?
So I think that the predicted depths that we have here are, like I said, like these are things that could be attainable today with the technology that is currently available. I think that there is a path in terms of both things that we can do on the signal side and things that can be done on the hardware side, where this could scale, 10x maybe to a kilometer depth. There is possibility to scale this if we have the advances in the technology. For example, it might be extreme to deploy such high-powered lasers on coastal waters, but in terms of if you're really trying to image deeper in the water, maybe you have this system mounted on a helicopter that can have these higher-powered laser systems that could have 100 kilowatts of power. That's your 10x right there. That gets you to a kilometer depth in water. So I think there is a path to scaling this system depending on the application that could easily be, we could push this system to imaging 10x farther in the water.
Yeah, the other thing I'd mention here is that, for example, the graphs that Aidan is showing on this slide are for an acoustic frequency of 71 kilohertz. Most sonar systems that operate today operate at an acoustic frequency of 8 kilohertz, for example. And obviously acoustic attenuation and dispersion is also much lower for lower frequencies. So this is just an optimal system based on the CMOS we currently use in the lab, but there is definitely potential to go to much larger depths if the application demands it by just tuning some parameters in terms of the acoustic sensors and frequencies we're using.
Great. The next question is from Anran about power. I want to make it a little bit more broader than the question he asked. Anran's question is, does the high laser power damage, is it of concern to living things? But I think the bigger question I also wanted to ask is the following, which is, in biological applications, people do these things, the power they use is much higher, but the pulse width is much smaller. So the question really is, can your laser, what kind of a boost there's so many things here, right? Like can normal drones carry a laser which actually can output these kind of powers? So can you talk more broadly about powering these relatively high-powered drones with these lasers on them?
Yeah, so I think something that you mentioned was that it also comes down to not necessarily just peak power, but it's, the size of the laser system is really limited by the energy output. And because we are using relatively short pulses, the energy output of these laser systems is pretty low. So if we do have a laser system that is customized for our application, where it puts out these high peak powers over low or short pulse widths, the energy output is small enough such that it should be able to be designed in a form factor that is compact enough to exist on, say, a drone. Especially, I think there's a ton of things to think about. Like you said, there's a lot of different axes to think about, where also you have these drone systems now that can carry 100 kilograms of weight. There's not only is the laser technology advancing where we can shrink these laser systems, but the drone technology is advancing where maybe they can actually handle more weight. So in both axes, I think we're going to see improvements in terms of being able to deploy the system on a drone.
Shao has a question where, can underwater image be generated accurately when there are movements appearing in the detected area? I guess the question really is, like, if right now it's a static S with metal, but if there is things which are moving like a submarine or even smaller, I mean, I guess bigger things doesn't really matter because you're operating at really tiny scales. But if there are smaller things like fish or animals which you're trying to image, would that work here?
Yeah, I think I would relate this to other imaging technologies like radar and stuff that are currently dealing with these exact same things. I mean, in radar, they actually use the movement of the object sometimes for their advantage in the image reconstruction. And I think because the time scale of the measurement capture is so small that the movement and speed at which these natural beings will move are small enough that I don't think that it would have a huge impact on the imaging.
Very cool. So maybe we'll let you finish the slides and then we can add the rest of the questions after that. Very, very interesting talk. So why don't we just let you continue?
Yeah, my last slide is kind of on some of the things that we've just been touching on. The project is still very young. So far we've really focused our efforts on studying the physics to develop a framework for scalable design. And we focused on producing preliminary results with this proof of concept hardware and computational algorithms. But there's still much work to be done. And here I list a few examples of some of the remaining research challenges. So first, on the transmit side, this is something that we were just discussing a little bit. There is potential advancement for the laser technology, and this could be in the form of reducing the size of the laser, customizing them for our specific application so that we can have higher power but maintain low energy outputs, all sorts of things that could be advanced on the laser technology side. On the receive side, like I said earlier, we currently use a single CMUT that we're mechanically scanning. Obviously, this is not something that is possible in the field because you want to have rapid, real-time measurements. So we need to have a large array of receivers, and we need to design interfacing electronics for these arrays. Also, there's a lot of work that could be done on, I think Ajay mentioned it in the chat a little bit, making these CMUTs multi-frequency so that we can dynamically adjust the frequencies to be optimal for our imaging scenario or the imaging application. So there's work to be done on the receive side. On the signal processing side, image reconstruction with surface waves. I talked a little bit about that, but that's an active area of research that we are currently working on. And finally, there's also interesting applications, adjacent applications of this technology, which was another question earlier. So one that is top of mind for us is communicating with underwater nodes. There really isn't a technology today that's readily available that allows for communicating airborne nodes to underwater nodes or vice versa. And this technology offers that, or could offer that bidirectional communication that is not currently available in a robust fashion. So that.
Yeah, this is great. We're going to open it up for questions. So I wanted to actually maybe ask Ajay a little bit about, maybe he can talk a little bit more about the hardware itself, like what it took to build the hardware, and what do you see as path forwards for miniaturizing it?
Yeah, so basically the CMODs that we use were initially deployed again for medical imaging purposes and were actually developed 2 decades ago at a research group in Stanford, Professor Pierre Curie-Jacob's group, and we collaborate with them to make these CMODs that we use. We are already in the process of building CMOD receiver arrays, as well as ASICs, like application-specific ICs or custom integrated circuits that we've taped out already. And later this year, maybe you'll see a paper from us about that as well, where we already have a bunch of receiver arrays that we've recently fabricated, as well as electronics that interface with it. One advantage of using CMODs is that they are MEMS devices that are completely silicon compatible as well. So you can monolithically integrate the sensors as well as the electronics, which is something that is very important when you are detecting pressures as low as we are. So for example, we're detecting pressures that are maybe a few dB higher than the mechanical noise floor of these devices. So very close to the optimal sensitivity that the CMODs can achieve. And in order to actually maintain the sensitivity, we want receiver electronics that can be tightly integrated with it so that we can maintain that sensitivity from the CMODs. And so this is definitely something that has had a lot of interest and is also now being commercially deployed in some healthcare systems by Toshiba and Philips, where they are now replacing their piezoelectric based ultrasonic probes with CMOD arrays instead. So I think we're definitely going to see a much clearer path forward when it comes to manufacturing these arrays at scale. For example, the 50 by 50 centimeter array that Aiden showed in his estimates is something that will have to be done in a professional fabrication facility and not so much at a microfabrication facility on the Stanford campus, for example. But so far, we just use the Stanford nanofabrication facility to design the CMOS that we have. And we now have a very stable recipe that we hope to replicate and scale up.
It's great. It's really impressive that this particular sensor can detect pressures which are that low. We have a couple of other questions. Laurel has a question which is about how large would the drone have to be to carry the laser and the array? And also the power supply. I think it's because heavier, I mean, if you're talking about 1 kilowatt or 10 kilowatt, you need a bigger power supply, and that means that it requires more power to carry it. So if you guys can talk a little bit about that.
Yeah. So in terms of how large the drone would be, I think what we've thought about right now is that the systems that we are using in the lab. I don't know if maybe I can go back and show. This is what our current laser system looks like. It weighs on the order of 50 kilogram. It's relatively large, but the reason for that mainly is because it's not custom for our application. It allows you to put out, basically it allows you to put out 4.5 kilowatts of peak power, of continuous power. And we are basically throwing away all the power that we don't want, which is a lot. So we have this general purpose laser system that can be used for a number of our applications in our lab, but it's not custom for what we are trying to do for this system, where we're really trying to put out, maybe we're trying to put out kilowatt power, but for less than a millisecond. So we don't need all of this continuous power. And I think having lower energy output, or keeping these peak powers high, but only for short amount of times, allows for reducing these systems to smaller form factors. But this really isn't something that is commercially available today. So I'm not quite sure to what degree the form factor would reduce. But I think it's important to keep in mind that the laser technology is rapidly advancing. I think I don't want to talk too much about it, mainly because I don't know too much about it. But if you look up like Viscal arrays and stuff like that, there's a lot of these newer laser technologies that allow for outputting higher power in smaller form factors. So there's a lot of interesting potential to use the advancing technology in our system. In terms of the power supply, I think that is another interesting thing to think about. I think, Ajay, maybe you want to talk about that a little bit.
Yeah, so the power supply challenge is definitely something we have to address, but it is not as big of a challenge as it seems at the surface, because our system is very heavily duty cycled. Because the laser light is literally just shining within the first few microseconds, and then we wait for a few hundreds of milliseconds almost to wait for the acoustic signal to arrive to the arrays. So even though we have a slightly large peak power, it is not continuous wave as Aidan explained. So that is something that we think is, again, not a prohibitive cost in terms of deploying it on a drone. And we still think that in an optimal system, we should be able to get it within like the 50 kg figure that Aidan mentioned. But obviously, as you can, I think, also get from our questions, this is something we haven't explored in great detail so far, because we were focused on just having a lab-based system that we could get working in an optimal manner, but is something that we do plan to address in the future. And hopefully we'll have better answers, more concrete answers for them as well.
We have a couple of other questions as well. I want to make sure that we get to them. Matthew has a question about, which I think is pretty interesting, which is, I think one of the places where this thing can be really useful is for imaging under ice, sheets of ice. But then you're talking about going through 3 media now. You're talking about air and then a sheet of ice, and then you're talking about water. So do you have thoughts on like how to potentially extend this system in those applications as well?
Yeah, this is an application space that I thought of about a year ago, and I think it's really interesting and possibly something that our system could scale to do. Like I said earlier, the propagation of the acoustic waves through these media, whether it be water, ice, air, is dependent on the acoustic impedance of the medium. And it turns out that the ice acoustic impedance is not like, it's more like, instead of being orders of magnitude different than water, like air is, it's on the order of like maybe 3 times the acoustic impedance of water. So really, you would suffer some loss going from air to ice to water, back to the ice, back to air. But I think in terms of the relative loss to the 65 dB that we're already losing, it's something that could be compensated for. And this technology could possibly be used for that. And something I also want to note is, because there is an acoustic impedance difference between ice and water, it is possible that maybe even this technology could be used for mapping the thickness of ice and monitoring the thickness of ice over time, for example, on the poles, to or basically to monitor global warming or something over long periods of time.
And that would probably make sense, a lot more sense, because if you're talking about 100 meters depth, that was definitely be in the ballpark of what you would see there. Couple of other questions from Benjamin. This is actually on the communication side, so it's a little bit more of like future.
Yeah. So I can answer Benjamin's question. So Benjamin asked whether we can communicate for the uplink and have something underwater shoot a laser as well. And that is something that is suboptimal because, again, as it mentioned, like you have a lot of scattering in the ocean. So instead, what we do is still rely on just the acoustic communication through water, which is why we think our system has potential for bidirectional communication, because we'd use the laser light when it's coming from the drone to the object underwater. But for the side coming from the object underwater to the drone, it'd just be purely sound. And we leverage the high sensitivity we have. One example I can also give about this is a SIGCOMM paper from a couple of years ago that was also using a multimodal system to communicate across this air-water interface. But they, again, just showed unidirectional communication, where they used an acoustic source to transmit sound to the water surface, and then used radar technology to detect deflections at the surface of water. But they were unable to go the other way around, that is from the drone to water. And that's a paper that maybe people can read if they're slightly interested in looking at communication across this air-water interface, and work that currently has been done, most of which has been just unidirectional communication.
A couple of other questions from Alex. Clearly there are applications here for the military domain, but if you guys can also talk a little bit about some of the non-military use cases, that will be helpful as well.
One application that I can mention maybe is that another project we work on is funded by ARPA-E, the Department of Energy, where we're doing sensing of things underground. But there is also a program where they're looking at having, for example, kelp farms or algae farms in the ocean for energy generation. And these need to be continuously monitored. And the idea is that you can have a way, if you have large amounts of data that you monitor, then you can build hybrids or genotypes of these kelp or algae farms that can be used for carbon sequestration, for energy generation. So that is one application. Other applications is stuff that Aidan mentioned in the introduction, where you could monitor coral reef health, for example, to look at the effects of climate change, even monitoring the thickness of ice sheets or other such things. But
I think
maybe Aidan, you want to think? Yes.
Outside of thinking about using this technology in water, we've also started thinking about how this technology can be used to do non-contact ultrasound imaging in the body. So, for example, if we picked the laser wavelength properly, such that the laser is absorbed at the surface of the skin, and that generates a sound wave that propagates into the body, like traditional ultrasound, reflects off of things in the body, and comes back, and we pick it up in the air with our high sensitivity CMUTs, then we could perform non-contact ultrasound such that you could image places that you might not be able to get an ultrasound probe to in contact. So for example, like burned skin, or if you're ultrasounding, if you're trying to image open wounds, or things like imaging during surgical procedures, stuff like that. I think there's a lot of potential for the technology to be used for that as well. I think this is something that Ajay always likes to remind me of, is that in medical imaging, it's important that you don't sacrifice too much to gain something. So basically, if we have this non-contact system, you'll most likely sacrifice some resolution. And that's something that might not be acceptable for most applications. So for example, this technology likely couldn't replace ultrasound imaging completely, because you would want the higher resolution that's offered by contact-based ultrasound. But it's really those application spaces where you can't get a conventional ultrasound probe to, that maybe this technology can help supplement conventional ultrasound imaging.
Two more questions before we can let you guys go. Keishan had a question on the time domain backpropagation algorithm, where it involves knowing the speed of acoustic propagation. And if you can talk a little bit about how things like wind and water waves and particles might potentially affect that.
Yeah, so the speed of sound in water, I think I labeled it on the screen, we typically take to be 1,500 meters per second. That's like, that's an average for the average water temperature. But, the temperature of water, the density of water changes as a function of depth. So there is some variation in the speed of sound in the water column. But as long as, and this is something that is also a problem in ultrasound imaging. So for ultrasound imaging, the speed of sound travels different, say in fat tissue versus muscle tissue versus, tumorous tissue. It travels different speeds in the body. So what they do is they typically take 1540 meters per second, and they assume that the speed of sound is uniform, and that produces okay imaging. But an active area of research in ultrasound is how can we try to use the data that we recovered to basically correct for these errors in the speed of sound, and create higher resolution images, correct for this error that comes about from having speed of sound different from what you assume. So that's something that we could also look into for our application, trying to adjust the speed of sound to optimally reconstruct an image. In terms of the air, we typically take it to be 340 meters per second. That's a function of the temperature, the humidity, and maybe that's something that can be calibrated. So you have a sensor on board the drone, and you say, okay, what's the humidity, what's the temperature, and then you say, all right, for our image reconstruction algorithm, we're going to use 330 meters per second instead of 340 meters per second, to do your image reconstruction. So that's another option that's possible.
One last question from Ethan. You mentioned about swarms of drones for future work. And that seems like there's lots of interesting things to be done there in terms of coordinating between all these drones and using image stitching. You can use compressive sensing. There's so much stuff to be done there. So can you talk a little bit about it and just talk about from a broad perspective?
A lot of these algorithmic challenges are being addressed in other areas of research. So for example, one hot area of research right now is using radar systems on drones and swarms of drones. And they're working on kind of the same problems. They're using simultaneous localization and mapping algorithms, SLAM algorithms, to try to basically understand where your drone exists in the environment. And if you have these algorithms running on the drones, you should be able to localize the measurements for each of them and possibly be able to stitch them together and stuff like that, and be able to utilize and combine images across different drones in a swarm of drones. So I think, again, it's something that's interesting and maybe something that we will be looking at in the future, but is a challenge that is already being actively researched by others.
Sweet. This is excellent, guys. You guys did an excellent job presenting the concept in a really accessible way. So thank you so much. Thank you so much for taking the time. And we're a little bit over time. So thanks again. And hopefully best of luck with the work. This seems very exciting.
Yeah. Feel free to shoot us an email if there are any questions that we couldn't get to, and we'll be happy to answer them, and even chat later if anyone is interested.
Thank you, guys.
Yeah, thank you.